present my work regarding black box estimation of differential privacy in machine learning. So I'm very happy to introduce this question and then some progress I did along with it. So this talk is based on joint work with two group of researchers. Yeah, so let me start with introduce the problem. So what's the problem? What's the question motivate me, and then I will give you a problem formulation. So um, the question that sounds very interesting to me is to present a user-friendly price analysis tool. So imagine you are a machine learning expert. You know quite well how to extract the useful information from the dataset, but you might not know how to show the extracted information preserves some level of privacy. So here, the the algorithm doesn't have to be designed with privacy in mind. So it doesn't have to be called a private algorithm. It might be just some machine learning algorithm or arbitrary um, randomized algorithm. Because that we know there are many algorithms that are developed before the privacy become central concern. But there are privacy and guarantee and not get like um, properly understand. So it's quite interesting to me to ask what's the privacy of them. So here the privacy we consider is just the property of output distribution. So we view it as the indistinguishability between two words. So in the real world, you will run the algorithm with the real data set D. And then there's an ideal world where you will run a sanitized version of this data set D prime. And then we say the indistinguishability here is just some distance between the two output distribution. That the output of the mechanism, the algorithm I'm running with D, and then the output of this algorithm I'm running with D prime. And then we see the randomized algorithm M is private. If the worst case the distance that overall allowed this real world ideal world pair is small. So under this kind of general privacy definition, so we can say that it covers most of the known standard privacy definition. So say for example, if you treat the distance matrix D as a statistical distance, and then you just reduce to the statistical security. And if you treat it as a hockey stick divergency, and then you come back to the standard approximate DP, that is epsilon delta DP. And then if you treat the distance as the trade-off function, so and you come to a modern variant of the DP, which is known as functional DP or Gaussian DP. And there are more examples like Renyi divergences, and then you get Renyi DP and so on and so forth. So yeah, so that's the privacy we want to study. So yeah, to get some like more concrete example, so let me present some randomized algorithm, and then which privacy guarantee actually are not well known. So the first example is the random projection. It's a quite well-known machine learning technique that used to do the random detect this dimensionality reductions. So yeah, so think of your databases as a vector, and then you want to use a random projector, which is modeled as a random matrix, to project these databases to a sub-dimensional space. So you project your databases to a lower dimensional vectors. And because this projector is randomized, so it sounds like the output random vector has some privacy because it's encoded in a randomized way, has some uncertainty. So what's the privacy of it? it sounds like the standard DP techniques too, for example, um, didn't study it widely. So another example is the approximate least square. So we know the least square. So you have a linear equation system, and you want to compute a least square solution. That is a vector that minimizes least square error. So approximate least square is like because your linear equation system is too large, and then so you want to first compute a sketch of this linear system using a random projector. And then you compute the least square solution of this sketch. So this shrink sublinear system. So what is the privacy of this approximate least squares output? Um, yeah, and then the privacy is defined with respect to dp or statistical distance or whatever. Yeah. So far as I know, it's like no study about this. And then another example is this stochastic gradient descent. So we know this gradient descent algorithm is an quite well-known algorithm to compute um, a optimization solution. So the stochastic gradient descent is just the randomized version of it. And then so its differentially private version is also quite known. But what about this middle ground, the stochastic gradient descent variant? It also has randomness. So in each iteration, you compute a subset of the data set, and over this data set, you compute the gradient. So here is the subsampling step, which is stochastic. And then you clip the gradient, you do further post-processing. Seems like somehow you amplify the privacy and then you compute the gradient. So it sounds like also have some randomness and it introduces uncertainty. So what is the privacy of it? So there are many such examples. So there are many machine learning algorithms. It sounds like come with randomness, but their privacy property actually is doesn't get a proper understanding. So my main motivation is that can we compute the privacy of them? So if they have some inherent good privacy, can we improve the guarantee, privacy guarantee with just a minor modification? Yeah, that's basically the motivation of this talk. To slightly concrete the problem. So the problem we want to answer is given a randomized algorithm, and you have a way to obtain a pair with real-world databases and its sanitized version D prime. Can we efficiently estimate the distance between this output distribution with provable accuracy and confidence? And then we can only black box access to the mechanism, and probably we can have a mild regular assumption on the M's, say the M's output is smoothness. So yeah, that's the main question I want to discuss in this talk. So so why this problem might be interesting? So there are some possible application and the natural follow-up question we can ask. So first thing is like it helps us to detect the, so it immediately implies that we can detect the privacy violation. So if there's a deployed mechanism which has a claim the privacy guarantee, and then if we can estimate the distance between the output distribution pair, that means like this give us a certified lower bound on the privacy. If this privacy loss is larger than what the privacy claim gives, that means like we have a privacy violation. So a second possible application is that we can use this estimator to estimate the privacy of a arbitrary randomized algorithm. So it's like if we think of this privacy of the algorithm, just the property of this algorithm, and then you can quantify that it's a number. So basically, you can get the number for each algorithm. So this itself is very interesting. It can help you to cover potential good private algorithm candidate, or it can also help you just like study the property of non-arbitrary algorithm. It is at least quite interesting to me. And then the third application is quite natural follow-up correction, although it might be independent, is that how do you make the algorithm more private? So if we know the distance between two distributions, how could we edit this output distribution to reduce the distance further? That is to make this algorithm more private. So yeah, there's possible application of this black box estimation problem. Oh yeah, please let me know if you have any question or any part is unclear to you. Yeah. Okay. So now I want to move on to introduce a black box estimation framework for differential privacy. So yeah, as the first step, we need to recap the definition of differential privacy and instantiate the distance between a pair of distribution using this hockey stick divergence distance. Divergence, it's not a distance. So basically, DP says that so a mechanism is epsilon delta DP that is for all possible neighboring pair um, that just slightly changing the input, then their corresponding output pair also just slightly change. So that's basically the high level idea. Um, so the distance between a pair of distribution here we define by something called privacy profile. So basically, so there should have a pair of a database D and D prime, and by a fixed epsilon, they give a smallest delta. So basically, you need to make this inequality becomes equality. Yeah, so we call this curve minimal delta. So basically, this blue curve. Yeah. So basically, our task is to estimate this blue curve. Yeah. So I'm not quite sure that if this minimal delta or they call it privacy profile is familiar to you. So probably let me explain more. So you can think of like a pair of distribution. They satisfy a set of epsilon delta pair. So all this epsilon delta pair can be categorized in this two-dimensional figure. So this epsilon delta give you a two-dimensional space. So this pair of distribution, there are some epsilon delta pair that is satisfied by this pair of distribution that is in this green region. And some of the epsilon delta is not satisfied. So they are in the red region. So there's a blue curve that define the boundary between the epsilon delta is satisfied and not satisfied. So that is the tightest characterization you can find. So we define this curve as privacy profile, or I just call it minimal delta. So minimal delta is just the treats the delta as a function of the epsilon. So for every possible epsilon, what is the smallest delta you can achieve? So that's a distance here that we want to estimate. Yeah, let me know if it doesn't make sense to you. Okay. So actually, this minimal delta can be defined in many different ways. So you can just represent it by the original DP definition, and there are some known identity for it. like hockey stick divergence, a privacy loss random variable, and just indistinguishability. So here in this talk, we introduced two identity. The one I called it Bayes risk based identity. I will explain later what does it mean. And if you can constrain your mechanism's output, it's just a Gaussian. It can be arbitrary Gaussian. It doesn't have to be the Gaussian mechanism output. And then you can represent your delta using some expectation of a fixed transformation of standard Gaussian. So it's also a very neat form. So that's a two identity we introduced here, and probably want to discuss in the following talk. Yeah, so let me explain more about this identity of delta based on the Bayes risk. So let me first give you a high level idea. So here, this minimal delta is defined as for all possible adversarial A, and then you want it adversarial to guess. So given the distribution either P or Q, so sorry, you're given a sample from distribution either P and Q, and then you want this adversarial to guess whether the sample is from the distribution P or distribution Q. And then, so you can represent the minimal delta in such form. So basically, to estimate the delta of epsilon, you're asking what is the indistinguishability of the Bath distinguisher. So you find the Bath distinguisher that help you to maximize the difference between these two, this probability and this scaled probability. So what the Bath distinguisher can do for you. And then, so we argue that this problem can be reduced, or this problem is just equivalent to the problem that you compute what is the misclassification error that the Bath classifier can give you for another problem B that is reduced from the original problem on the left-hand side. Yeah, so that's yeah, I'm not quite sure. Yeah, let me know if you have a problem about that. So basically the intuition is that if you want to compute the delta, that is measure the indistinguishability, that is equivalent to measure another type of indistinguishability. So those two are the same. So you can also represent it as computing the indistinguishability of a game. That's the same as compute a misclassification error of a classification problem. So that's a high level idea. So here this classification problem is known as Bayesian learning problem. So first, so let me explain what the Bayesian learning problem looks like. So basically, you flip a fair coin B, and then if the fair coin is 0, and then you get a sample from the distribution denoted by this. I will explain later how we get it. If you get a coin 1, and then you get and then you get a sample from the distribution Q, and then you find this sample to the binary classifier, and then this binary classifier will give you a label. So what is the class of this sample? And then the misclassification error is just the average error that this classifier made for this learning problem. Yeah. So more formally, so we can get such an informal theory. It says like let P be the Bayesian binary classification problem with likelihood. I'll explain it. So, but basically it's a distribution parameterized by the parameter epsilon. and another distribution y, and with uniform prime and 0, 1 loss. And let H star be the optimal Bayes classifier for this problem. That is above the classifier that has the minimal error among all possible classifiers for this problem. And then the R of H star is the risk of H star. So it's basically that's the misclassification error of this best classifier. And then your problem of computing this minimal delta is reduced to compute the misclassification error of this best classifier. Yeah. I'd like to get some details of why these two are equivalent. So basically the idea is like we want to represent this delta to some statistical distance. That's the first step. So that's by definition, the minimal delta looks like this. And then you extract the scale e to the epsilon out, and then the inside part will look like this. So yeah, I bet this quite similar. You felt similar to this thing, so it's very similar to the statistical distance. If you treat the first term as the probability of some other random variable, right? The probability of some event of other random variable. So actually, it's quite easy to construct such a random variable. So here we call it x bracket epsilon. So it's a mixture of the two distribution. So with probability e to the minus epsilon, they just output x. So that if you get a outcome from the sport of x, and then the probability of this x bracket epsilon is just the e to the minus epsilon times the probability of x equal to this outcome. So it matches this part. And then for this part, you just like give it for free. So the statistical distance between this x bracket and the y actually can be represented in such form. So because y, we assume that bottom mark that is not a possible outcome of the random variable y. So it's not a possible outcome of a random variable y, so you can write it in such form. So we notice that these two actually have the common item, and then you can just rewrite and then write the delta as just some function of the statistical distance between these two random variables, where the x bracket is what you coined. And there's a known folklore lemma, so which says that okay, the statistical distance between a pair of the random variable, a pair of the distribution, is equal to the Bayes risk. It's some like Bayes risk. How to say? It's like so. Okay, so let's say there's a classifier, but the best classifier for trying to classify this pair of distribution x bracket and a y. So the statistical distance between this pair of distribution is equivalent to some scale and some linear function of the misclassification error of this classifier. Okay, so basically, to compute the statistical distance between a pair of distribution, you can instead compute the Bayes race of this classifier, which is to classify this pair of distribution. So when combining both parts, we get this final identity. So basically it says to compute the delta of the epsilon, you can equivalently to compute the misclassification error of the Bayes classifier for this pair of distribution. So that's the identity. Oh, yeah. And then once we have the identity, actually the black box DP estimation type become like easier to think and easier to solve. So we first describe the problem statement. So the problem statement is like the given a mechanism and it's just input-output space description. Oh, we want an efficient algorithm that give you a good estimate of the delta, this minimal delta, this curve. And then the desired property we want is that this efficient algorithm A only black box access the mechanism. And we want this algorithm A doesn't have too much prior assumption on the mechanism. So this algorithm A doesn't make a minimal assumption on M, and it should give a tight estimate of the delta, which means like you should give an estimate with proper accuracy guarantee. So that's a desired property we want. And then when we notice that this estimation of the delta problem can be reduced to the Bayes risk estimation problem, we instead ask the following question. So basically, it's just like given a Bayesian learning problem B, we want an efficient algorithm A outputting a good classifier. So this classifier make minimal data assumption. It shall be better a non-parametric classifier. It doesn't try to make an assumption on the data structure or something like that. And it should have asymptotic optimality. So we know that finding this best classifier or this optimal Bayes classifier is quite hard, but we want to have a classifier that approximates this best. So its misclassification error converts to the Bayes risk as your sample size increase. And then for such a classifier, actually, we have a very good candidate, which is called k-nearest neighboring classifier. So the machine learning community studied a lot and has a lot of very good property. So first, the k-nearest neighbor is non-parametric. So that gives us this black box property. And then second is like we want a minimal assumption on the mechanism. So we don't want the classifier make too much prior assumption on the mechanism. So because k-nearest neighbor is non-parametric, so it satisfies two. And then third is like we want to get a tight estimate of the privacy spectrum. Because k-nearest neighbor is knowing that it's approximate to the Bayes classifier, the best classifier with the good convergence rate. So it converges fast to the best classifier. So that theory can naturally be transformed to a accuracy guarantee of the tightness. Yeah. So that's basically the part for the black box estimation for differential privacy. So so basically to summary, you can construct a classifier based estimator and then it give you a good estimate of the differential privacy parameter. Yeah, and then for
Sorry,
the sorry, go ahead.
can you like explain a bit more on how this convergence work? Like,
Oh,
is
you
it
mean this
guaranteed that, yeah, is it guaranteed that you will find this,
yeah,
like
sure,
kind of get a lower bound on the
sure,
privacy, like loss, like through this KN classifier?
sure. So let's look at this identity. So basically, we're saying that okay, so now we have this pair of distribution. Although we don't know its actual or what does this actual distribution look like, but we can get sample from it, right? And then the goal is like we want to so ideally we want to find the best classifier among all the classifier that can give you a good that give the minimal minimal error that can that can correctly label the sample mode. And now the question is, okay, we cannot find this of the classifier if we don't know this distribution. Once we only get the sample from it, and then we don't make too much assumption on the structure of this distribution, it's very hard to find this of the classifier. And then the way we do that is to find the classifier that approximates the BEPS. So the approximate BEPS here means that you have a classifier, and then we can construct this classifier just from the data, and then we can compute and estimate the classification error of this classifier, and then we can bound the distance between the error of this classifier and then the best classifier, this Bayes classifier. Yeah, I'm not quite sure. Does that answer your question? And then once you have those, and then you can replace this Bayes risk with the risk of the true classifier you constructed, and with the additive error. And this additive error will become additive error of this delta scaled by this constant.
Okay, so in this like KN algorithm, I think there's some like distance metrics, right?
Yeah, exactly.
And how does
You
that
need to
relate?
define the distance metric. So so in practice, I tell this job to use this L2 norm. Yeah.
Thanks for the clarification.
Okay. Yeah, I mean, in practice, actually, it's quite interesting to study, say, what if you use a neural network as a classifier? You might not have a theoretical guarantee because of the complexity of the neural network. But actually, I tried some, so it also gives a reasonable estimate. So if your task is just to audit if it's a job to find the privacy violation. Actually, I think neural network is also a good way if you just want the lower bound and not the tight bound. Yeah. Okay. So yeah, and then for the second part, so I want to discuss the black box estimation of the F differential privacy. So for this part, I'll just to go over the high level idea. Um, yeah, but I think it's very interesting. So to recap, we need to define the binary hypothesis testing. So it says like you have a two output distribution, and then you only observe a single sample from one of these two distribution, and then we want to decide which distribution this sample is from. And then a test for solving this problem is called a binary test. So it just input this sample, and then this output is either the hypothesis zero, that's non-hypothesis, or it's alternative hypothesis. And then we define two type of error. So with respect to a task G. So which says like what is the probability that your sample is from the distribution P, but you wrongly label it to one. That is a false positive. And then the type 2 error. It's like, what is the probability that your sample is from distribution Q, but you wrongly label it to zero? So this alpha beta actually can give you a curve, so which we call it a trade-off function. Sorry, it's not a trade-off function. It just to give you a curve. And then the trade-off function is curve for the best test to distinguish P and Q. That is the best test that given a fixed alpha that it can achieve the minimal beta. And actually, you found that this curve is quite similar to the one of the minimal delta curve or privacy profile per a curve. You just like reparameterize and then call it a trade-off function. And then actually it's turned out that these two curves are equivalent if you can construct this trade-off function, and then actually you can use that to construct this minimal delta. So that's a very interesting thing. And then F differential privacy says like a randomized algorithm is FDP if for all the neighboring databases, their trade-off curve uh, is is like at least lower bounded by some reference trade-off curve. So if you can think of like this trade-off curve is the distance between this pair of distribution. It tells you like how hard to distinguish this pair of distribution. So how close this two distribution is. Yeah, and then so you can think of like this function f is a lower bound of such distance. It says like your distance is at most such large. Yeah, yeah, but why did they use this lower bound? Because like the basket case is this this line. It's like if you are two distribution are perfectly equal, and then you get this line. And then if you are different, and then you get lower and lower, so they become a lower bound. Yeah, but yeah, so they have the same meaning conceptually that basically says, if your distance is small, and then you should get higher. Yeah. So the thing we want to mention here is that this F differential privacy is characterized by this task, so by this trade-off function. That also ask you to compute some difficulty of distinguish two distribution. And then, so it turned out that actually these three difficulties, they have different form, but actually they are equivalent. So uh, if you can find the best distinguisher for this indistinguishability problem, and then you can use that distinguisher to construct the best task that give you the trade-off function. And also equivalently, that means like you can construct the best classifier and then compute the misclassification error of this best classifier. So the takeaway and the main message I want to present here is that uh, these three questions are equivalent. So to estimate FDP, you can also reduce to the Bayes risk form. You can also get non-identity for the trade-off curve in terms of the Bayes risk. So that's the idea.
So one question, so for this
Mhm.
classifier, is it like responsible for also choosing the input to the mechanism? Or like how do you
All
choose
right,
the
good. Oh, you're saying that, so please clarify me if I misunderstood. So you're saying that so because the privacy is defined as the distance between the worst distance between over all possible pairs, you're saying like how do you find this worst neighboring input?
yeah.
Oh, that's a very sharp question. So uh, that back up to the estimation formulation we have. So far we can only estimate the distance between a pair of distribution. So that means like uh, you can get an estimate of the pairwise distance, pairwise privacy, or data dependent privacy, but that don't naturally yield a privacy estimation of the privacy of the mechanism. You also need some like monotonicity or some like ordering structure over the input pair. So that means like if you only have this estimation, you can only have the use it for auditing the privacy. So to really to argue to convert it to a privacy argument, you need more work. You need more assumption. Yeah. Okay. So now that we can estimate the pair of the distance between a pair of distributions. So what's a nest? So I want to show some like application. So recall that my main goal, so my main motivation is to understand deploy the privacy guarantee of an arbitrary randomized algorithm. So does this estimation tool give me this? Actually no. So you can use it to detect the privacy violation. Um, you can estimate the privacy algorithm in certain cases. So as Daniel just mentioned, you need to construct some like establish some monotonicity of the input of the algorithm. But it's got restricted. And then yeah, and you can also try to upgrade the existing algorithm to make it more private. Now you know how to estimate the privacy, estimate the distance between a pair of distribution. You might want to edit this output distribution a little bit to make their distance smaller. So that's something we can do. But these are also except of the first point, the second two you need further study. So they are kind of like independent problem because they have like kind of independent component you need to study further. Yeah. Oh, so the first day application is detect the privacy violation. So I show here a simple Gaussian example. So here, this blue curve is the FDP distance between a pair of Gaussian, and then so they have the same variance, and then the first Gaussian with zero mean, and the second Gaussian with mean 0.5. So one is just a shifted version of the another. And then we want to uh, use the estimation to audit it. So this orange curve give you a loose estimate using field sample, and then we will use this coarse estimate to identify the gaps that maximize the reference curve, this claim curve, and then the estimate curve, and then we will use more samples to get estimate of this exact point. And then because of the property, the tightness property we just discussed, and then we can use the sample size to construct a confidence region. So here there's to estimate this point N2, we run this mechanism 10 to the 3 time. So run this Gaussian's output 10 to the 3 time. So it gives you a large confidence region. So it cannot distinguish us from this reference curve. But once we get more and more samples, this confidence region shrink and give us more confidence that this claimed curve is violated because so this confidence region doesn't have an overlap with this claim curve. So that one example of how can you use this estimation to estimation of one pair of distribution to audit the mechanisms claimed privacy. And then we also tapped on the DPFGD algorithm. So in this example, what we did is that you run this DPFGD algorithm using a Python package called allPickus, which set up some with so this theoretical upper bound and this delta parameters. And then we use this estimate to get the lower bound of the estimate. So it turned out that this bound, although it looks loose, so first is because this upper bound actually is not tight. But the second is that actually we are in the black box setting, so we have restricted information. So the estimate is not tight. But it turned out that this tightness, although it's not tight, is still comparable with previous work, which make more assumption on the mechanism. So they use some auditor that know the mechanism family. They know this tacit algorithm is a DPSGD algorithm, and then they inject the Gaussian noise. Because of it, actually, your output distribution has some structure, and then you can take advantage of this structure. For our method, we don't assume such knowledge, and then it still give comparable and tightness. And then the second application, so I use this estimator to estimate the
Sorry,
price.
may I ask,
Yeah, sorry.
like, what's
Sure.
the reason why like your estimate, does it like theoretically converge to the um let's say the
Mm-hmm.
Python package is implemented correctly. So
Mm-hmm.
if you like run it infinite number of times where it converge, or is there
Mm-hmm.
any reason why it like won't converge?
Okay.
Theoretical.
Yes. Yeah. Okay. So I think that there are two things I didn't mention that. So first thing is like so here it is this topic they compute this up on using a how to say using this privacy composition. So it's like their pricing model actually is that the adversary could say every intermediate gradient, not the gradient. So so but the actual privacy we want is like the adversary can only say the final model. So, so that means like there's already a mismatch of the actual privacy we computed and then the theoretical accuracy, privacy they compute. There's a one mismatch. And then the second thing is the output of the DPSGD is a model. So basically, we are asking what is trained mode, what's the privacy of this trained model. So the trained mode has so many parameters. If you directly audit estimate the privacy of this trained model, that you estimate a pair of distribution in super high dimension. So to make this step efficiently, actually we do a very brutal projection. So we project this train parameter to one-dimensional space. So this part of post-processing actually makes this estimate way more loose. So that's why there's a gap between the theoretical and the estimated one.
I see, thanks.
Yeah. So yeah, it's quite interesting to say how to directly estimate the privacy of high dimensional space, but due to the curse of the dimensionality, it sounds like not a trivial task. Yeah. Okay, and then the second application is let's get back to the start point of the motivation. We want to understand the privacy of some randomized algorithm, which privacy is not properly understood. So this random projection and approximately square. And then this red star actually um, is produced by the estimator. And then I found them they have like proper privacy. And then I just like handcraft compute the theoretical curve later, and then find that they're tightly matched. So basically, there we show the tightness of the estimation, and then here the output is not in one dimension. So if your dimension is reasonable, so then the estimation is still converges to the true theoretical curve. And then the third application is like a natural follow-up question once you have the estimation of uh, estimation of the privacy of the existing algorithm. because they are not designed with privacy in mind. It's quite natural question is how to upgrade the privacy of it. So I think the estimation um, um, motivate us to do so, although it doesn't give you a um, direct answer. So the price analysis of the approximate least square actually is more involved and interesting, but I don't have time now, but please refer my paper. But I do want to discuss this random projection. So just to recap, the random projection is like you have a high dimensional vector or high dimensional matrix, and then you want to use a random projector to project it to a subspace. And then this sketch in the subspace shall still preserve some useful information of the original databases, like the length information. And then you can compute the dot product and some like the cosine similarity, this kind of useful information. So using another identity I mentioned, actually, you can compute the curve analytically. So basically, the theory says, okay, if you are giving me a pair of random projection output, and then your distance between this pair of output is only determined by the leverage score of the row that differ these two databases. So the leverage is a quantity. It's well known in the statistics. But basically, it quantified how important this record is with respect to the database SD. And now you can compute it. So they basically say if you are satisfied the privacy like this, and then you are done. So this random projection already gave it. But if you are not happy with it, and then you want more private, you want more privacy, what you can do is that you compute a desired so you set the desired price level you want, and then you use that to compute the largest leverage record this database should have, and then you regularize the databases such as its leverage match this threshold, and then and then you will do the random projection on this leverage databases. So that's basically the idea. So how do you upgrade? How do you upgrade a random projection algorithm to a DP mechanism? Oh yeah. So so Uh, I actually they study the privacy of random projection. We are not the first to work. There's a Folks paper did it, I guess, like 10 years ago, and probably more than 10 years. And then there's another paper, increase analysis of it. And then we further increase it. So we further improve the analysis using the method motivated by the estimation. And then here, the pair, so this table reports the accuracy of this random projection DP mechanism. So this pairwise deceleration and dot product ratio, which measures how close your noise is the distance compared to the original distance. So closer to one is better. And then it showed that we have a better accuracy compared to the previous work. Oh yeah. And then, yeah, I think it's a good time to conclude. So what we did in this talk is like we are discussing a question that how to understand the privacy of deployed machine learning algorithm. So this algorithm may not be designed with privacy in mind. And then towards this goal, we developed black box estimator for DP and FDP with provable final sample guarantee under mild smoothness assumption. And then we show that this tool can help us to audit the deployed mechanism. And then we also use it estimator to study the privacy of some non-standard machine learning method. So those methods is non-standard in the way that they are designed without privacy in mind, but actually they give some like interesting privacy property. And then we also show that combined with estimation with some analogical result, how could you upgrade existing algorithm with stronger privacy guarantee, but with just minimal change? Uh, yeah. And for future work, I think black box privacy estimation still has a lot of to do. So first, as we just discussed, it seems like not a trivial problem in the high dimensional setting. And then second is like, how do you estimate the privacy more efficiently in terms of the sample complexity and then the running time? And then probably the third directions like you can use some other foundations like learning theoretical foundation or other foundations to reduce the estimation problem to some known field, and then that might yield some more interesting estimators. And then another direction is like how to analyze using this uh, estimators to analyze and upgrade widely used algorithm without a proper understanding of the privacy. So it's some like interesting topic like study the privacy of stochastic gradient descent, not this DPSGD, just stochastic gradient descent, and probably large language model and other randomized linear algebra method, and automatic privacy upgrade, and get a practical tool chain. So those are some interesting direction to further explore. Uh, yeah, thank you. I think that concludes what I want to share. Please let me know if you have other questions.
Yeah, thanks for the talk. Just
Okay.
wondering, like, so here you are just assuming like black box access to the mechanism. Let's say let's say the mechanism is like a machine learning model, and you can actually retrieve some like intermediate, say, evaluation like data, like some data in like up, say after like
Mm-hmm.
several layers. Then
Mm-hmm.
with this information, do you think you can like achieve a better bond, or they are not
Yeah.
very useful?
Actually, that's a very interesting question. So, I haven't explored it enough, but so let's say your output is just a let's say a training model, and then you want to study like how private this training model is. Yeah. First, I do believe that this structure give you some information, and then one possible thing I'm trying to do is that. Let's forget about this theoretical guarantee first. Let's just say if we can have a neural network-based classifier can extract this structure and then use this structure to try to distinguish these two distribution, like the distribution over the trained model. We know that. So what I know is like, okay, you have this convolution neural network. So there's no this class of neural network know quite well how to extract these images features. And then we have this large language model that is uh, what's the I can't remember the name. But you have you have a specific class of neural network that's good at extract the structure of the language and then image. But are there a good class of neural network that are good at extract the structure of the neural network itself? If you can extract the feature of it, that is kind of very efficient um, dimensionality reduction. And then you can try to distinguish the distribution between this feature. I think that's a quite interesting, and I think it's promising direction. But I don't know too much about it.
Yes. Yeah, thanks. So basically, it solves the high dimensional setting
Yeah,
problem.
yeah, exactly. So I think like why with the curse of the dimensionality, and then people still can do well in the high dimensional setting, is that actually the effective dimension is not high. The hard things like it might not be easy to extract the feature to extract these effective dimensions. So if you have some classifier combined with this extractor that can effectively reduce the dimensions, that will be very interesting.
Okay, that's cool. And can you show us a link to the paper, maybe?
Oh yeah, so this talk combine three work I did with my collaborator. So here's a reference for them.
So I'll stop the recording.